Imagine you're blowing up a balloon. At first, it stretches bit by bit, but then one more puff and boom, it pops. In a titration, we gradually add one chemical to another, and just like with our balloon, there's often a point where a small addition triggers a big change. This is real chem. As we add air to a balloon, it stretches gradually until at a certain point, it bursts. In a titration, we gradually add a base to an acid, and with each addition, some of the acid is converted to its conjugate base. Step by step, the acid is transformed until we reach the breaking point, when just enough base has been added to completely react with all the acid. Let's take a closer look and see how this process unfolds. We'll start by titrating a strong acid with a strong base, and then switch to a weak acid titration. In both cases, the acid is placed in a flask and the base is added gradually. For the strong acid and base, we'll use hydrochloric acid, HCl, and sodium hydroxide, NaOH. In solution, the key reaction is shown here. Let's examine the titration curve. At the start of the titration, the pH is strongly acidic due to the excess hydronium ions. As hydroxide ions are gradually added, it neutralizes more and more of the acid. When just enough hydroxide ions have been added to fully react with all the hydronium ions, the pH reaches 7. This is called the equivalence point. Beyond this point, any extra hydroxide ions makes the solution basic. The equivalence point is easy to spot. It's where the pH suddenly jumps from acidic to basic, as sudden as a balloon bursting. Now, let's examine the titration of a weak acid, acetic acid, with a strong base, sodium hydroxide. We'll use the same volume and concentration as in the strong acid, strong base titration. Now let's compare how the titration curves differ. First, a weak acid starts with a higher initial pH than a strong acid because it's only partially dissociated, producing fewer hydronium ions. As a result, its pH begins closer to neutral. Next, let's look at the equivalence point. This occurs when the moles of base added equals the moles of acid originally present in the solution. Since the concentration of our weak acid is the same as that of the strong acid, it takes the same volume of base to reach the equivalence point in both cases. But while the volume of base needed is the same, the pH at the equivalence point is not. This difference comes from the products of the neutralization reaction. For a strong acid, neutralization produces only water. At the equivalence point, all of the strong acid has been converted to water, resulting in a neutral pH of 7. For a weak acid, however, neutralization forms its conjugate base, A-. At the equivalence point, all of the weak acid has been converted into its conjugate base. Since the solution now contains a weak base, the pH is basic, greater than 7. The titration curve also behaves differently before reaching the equivalence point. Instead of producing only water, the reaction with a weak acid gradually forms its conjugate base, creating a buffer that resists pH changes. This is called the buffer region. At the half equivalence point, half of the weak acid has been converted to its conjugate base form. Here, their concentrations are equal, meaning the pH equals the acid's pKa. Titrating a weak acid introduces unique considerations: a higher initial pH, the presence of a buffer region, and a basic pH at the equivalence point, all highlighting the distinct behavior of weak acids and their conjugate bases. Just like that balloon bursting after one last puff of breath, the titration curve shows us when the critical points are reached, or, more importantly, are close to being reached. By analyzing and understanding this curve, we can monitor for critical changes in water systems, control industrial processes efficiently, and develop new pharmaceuticals. Chemists should never be surprised when the balloon bursts.